The last section in this chapter that we're going to learn about is how to do a confidence interval on a proportion. Now, just a reminder, sometimes I do abbreviate confidence interval by CI. I watch a lot of true crime. Also stands for, what does it stand for? Confidential informant. Anyways, okay. So again, a reminder that these little hat things here mean estimate, right? So the first thing that we're going to talk about is proportion, meaning fraction. So whenever you see proportion or fraction in any of the homework problems or on an exam, we're talking about a proportion, right? So if I have, 12 people out of 100 who are engineering management majors in a class of mine, then the proportion of engineering management majors would be 0.12 and so on. So now this X here, this X, we're going to get an estimate of a proportion from our sample. So N is just the number in our sample as per usual. X is just the number observed of whatever the thing is that I'm getting a proportion estimate for. So 12 students out of 100 students would be, say, 0.12, which I said might be, for example, the number of engineering management majors I have in a particular class. We already know what the other components are in this formula here. Once we know what p hat is, we already know what z sub alpha over 2 is. We're going to use that for a two-sided confidence interval. And if we want a one-sided lower or a one-sided upper, we're going to be using z sub alpha and z sub alpha. You might remember we used those early on when we were doing a confidence interval on a population mean. So, and also once again, we have a function in our calculator that will do all of this for us, which is really quite nice. So let's do the example here. The example says, we've got 85 of these engine crankshaft bearings and 10 of them have a defective surface finish. We want to construct a 95% two-sided confidence interval on the proportion for P, and I probably should go here, the proportion or fraction of bearings that are defective. The first time I ever noticed that kind of was an incomplete information. You might hear the kids next door playing because it's a beautiful day here and they're so cute and I don't want to close the door. So you might hear some fun little voices laughing here. Okay, so let's get our data out of this one here. We have got a sample here of 85. And the number in the sample, because we're interested in the proportion defective, that is 10 right here. We know by when we see 95% two-sided confidence interval, we know then that our alpha is going to be 0.05. And so now what we can do is by hand, and also we can do it using the calculator function. So by hand, we're going to have P hat is X over N. So that's 10 out of 85. So that's going to be 10 out of 85 minus, what's our Z alpha over 2? Well, if alpha is 0.05 and alpha over 2 would be 0.025. And we already know that from the past as being a 1.96. As a reminder, if you're not sure how to get that, you would use the inverse norm function, area below, which would be 1 minus 0.025, 0 and 1. That's how you get that. Another reminder, if you have a calculator that says left tail or right tail, and you want to mimic exactly what my calculator does, you want to set your calculator function to left tail so that that first argument is area below. Just a few reminders here. All right, so we've got everything now. So we have 10 over 85, p hat minus 1.96 multiplied by the square root of p hat, 10 over 85. And then 1 minus 10 over 85 is going to be that would be 75 over 85. I hope you can figure that one out on your own. If you can't, maybe this isn't the right major, right? N is 85 here. And then when you crunch all that together, you're going to get 0.0492. Now notice there's no units on this because we're talking about the lower bound and upper bound of a proportion here. If we do the upper bound, we'll have 10 out of 85 plus 1.96 times that big term there, 10 out of 85 times 75 out of 85 divided by 85. And that works out to be 0.1861. And so now what this means is we would be able to say to ourselves or our boss or on an exam that based upon the sample data, those 10 bearings here, or the 80 bearing, 85, excuse me, and the 10, the probability that the interval 0.0492 up to 0.1861, the probability contains the true proportion defective. Remember, that's P. P hat is the estimate. This is the true, which we don't know, would be 0.95. If I want to do this in the calculator, it's very easy to do. I just go to stat test 1 proportion z interval. So I go stat test, and then I scroll down and I find 1 proportion z interval, not z interval, right there, 1 prop z int, boom. And then it will prompt me. So X in this case was 10. We had 10 defective bearings out of 85. And we want a confidence interval of, it's already in there as 0.95. And then when I hit calculate, it gives me exactly those values that I just did by hand. The first part is 0.04915. So to 4 decimal places, that would be 0.0492. Because this 5 makes me round the 1 up to a 2, and then I get 0.1861 to 4 decimal places because this is a 4, so this one remains the same, and so we get those values there. Easy peasy. Now, just like with when we did a confidence interval on the population mean when we assumed that we knew what the standard deviation was. We also went on to say, well, what if we want to be a certain amount close for to be close to the true proportion? So there's actually, the next 2 slides really are going to help you with a couple of homework problems. So this first slide says, suppose we want our estimate of the true population proportion. So a reminder that this is the true, it's the true value. We don't know what it is. P hat is the estimate. We want to be less than a specific distance from the true value. So we want to be a certain percentage confidence that the true value minus the estimate is not more than E. So I'm going to give you that, the text is, or you're going to come up with it yourself. This is what the formula is that we would use. Now, if we wanted to, if we don't care, it says right here, if we don't care what the P hat is specifically, what we're going to do is, I feel like I've got these out of order. Let me just double check this. 22, 23. No, we are just fine. There we go. And so if what we would want to do, we would take the first derivative with respect to P, set it to 0, and solve for P. So watch, this is exactly how this would happen. So here, we're going to use this formula if we estimate P by some initial P hat. Now that seems kind of weird, right? So let's back up for a second. I want to know what N should be so I can be a certain amount close to the true value, right? But basically it's saying take an initial value of P hat, maybe a super small sample, maybe an N of 5, use that P hat, plug it into here, and then you'll get the N that you really should use to be that close. So it's kind of iterative, right? So you start out with a small N, get an initial P hat, and then solve for the true N that would get you closer. It's kind of weird, right? This is the formula we're going to use there. We're going to use this formula if we don't care. So use this formula if no initial estimate is used, all right? So what you're going to find is that this value here is going to be bigger than this value here, I want to kind of point that out, all right? That n here will always be bigger than this n here, just so you know. So how did we go from here to here? Well, if what I want to do is whenever I want to think about it, whenever you want to maximize something, remember from calculus, so I'll write this from calc, to maximize something. So what I want to do is maximize this n. We take the first derivative and then set equal to 0 and then solve for whatever parameter we want, right? So let's do that here, all right? So what I'm going to do is I'm going to take this formula right here and I'm going to say I'm going to take the first derivative with respect to the true population proportion here. This will be treated as a constant, right? So, well, let me rewrite this. Let me rewrite this so it's a little bit easier to see, all right? If I expanded this, I'd have z alpha over 2 squared over e squared, and then we'd have times p minus, same term, z alpha over 2 squared over e squared, p squared, right? So if I take the first derivative with respect to p here, what do I get? I get this as a constant, z alpha over 2 squared over e minus e squared, z alpha over 2 squared over e squared. Then the first derivative with respect to p here would be 2p. And then what I'm going to do is I'm going to set that all equal to 0. And then what I'm going to do is I'm going to set it equal to 0 and I'm going to solve for p. So let me collect my terms here. So we'll have z alpha over 2 over e. I'm just rewriting it a little bit differently. And that would be 1 minus 2p equals 0. Now I'm going to solve for p. If I divide each side by this, I end up with 1 minus 2p equals 0. Then I end up with 1 equals 2p. And then I end up with p equals 1/2. So if I want to maximize this formula and I don't care about what p hat is, that's where the 0.25 comes in. Because if p is 1/2, then we get z alpha over 2 over e squared times 1/2 times 1 minus 1/2. So we have 1/2 times 1/2, which is 1/4, which is where we get the 0.25. I just wanted to point that out because sometimes it's a little confusing about where that comes from. So a reminder here, just a couple of reminders, p hat is equal to the number observed over the sample size. And that p hat is some initial value that we're going to use over here. And then we're going to solve again for n to get the appropriate value. So why do I go into this detail? Because you're going to have a homework problem that presents as follows. Something very similar. So let's go at this one. I'm going to use, what color haven't I used here yet? I'm going to use purple. All right, so we've got 85 crankshift bearings. 10 have a surface finish rougher than specifications allow. Okay, if we wanted to determine how large of a sample is required, if we want to be 95% confident that the error in using p hat, so if the wording is this way, is less than 0.04, we're going to use this formula. So if the wording is like this, we will have as follows. We know that z alpha over 2, alpha is 0.05, so we have 0.05 over 2. We already know what that one is. That's 1.96. We know that e, they just gave that to us, is 0.04. It's a little bit confusing when they say less than, just use the value of 0.04. We know that our initial p is going to be x over n. So x is 10, n is 85. Okay, so that's our initial P hat, so let me write that down, P hat initial equals 10 over 85. And so now they're saying if we had 10 out of 85 on this initial shot, how big would n really have to be if we wanted to be within 0.04 of the true value? And so here we would just plug things in. We would plug in 1.96 over 0.04 squared times p, which we're going to use p hat in this case, 10 over 85, and then 1 minus 10 over 85 is 75 over 85. And then that n will work out to be 249.2, but we know we're always going to always round up. And so our answer would be 250 bearings is what we would have to sample if we wanted to be within 0.04 of the true proportion, given that our initial estimate is 10 over 85. Now, conversely, if we don't want to do a p hat at all initially, here's what we can do, and I use a different color here. If we want it to be at least 95% confident that our estimate, again, p hat, of the true proportion was within 0.04, regardless of the value of p, we use this formula. And so now when we plug in, we get 1.96 over 0.04 squared, and then just times 0.25, which I showed you on the previous slide where that came from. And look at the difference. This ends up being 600.3, which again, we would round up. So it would be 601 bearings. So if you take an initial estimate, which gives you kind of a baseline, and then you want to compute n to be a certain percent confident that you're within a certain distance, you add a less value than if you don't take an initial p at all. Anyway, so this would be the more conservative way to go. This would be the less expensive way to go. Okay, that ends chapter 8.